Have you ever looked up at the night sky and wondered, why is space black? If there truly is an essentially infinite number of stars, then that means any line of sight would eventually end on the surface of a star. You can see this in Space Engine. Literally click anywhere on the screen and go to the object and it will be a star. So instead of looking like this, the sky should look like this, but it doesn't. This is called Olbers' paradox. In this video, I'm going to show you how this paradox is resolved and try to figure out just how black the night sky really is. And in doing so, we'll run into another question. Is it even possible to see 100% blackness, even if there were no stars in the universe? So in order to understand this paradox, first we need to be clear about what we think we should see if there are a lot of stars in the universe. You may be thinking, well, most of the stars are far away, so they're just really dim. That's why we don't see them. And that's true. The total light we receive from each star decreases with distance. But at the same time, the star also appears smaller by exactly the same factor. These two effects cancel, so the apparent brightness of each tiny patch of a star's surface stays the same. For example, let's look at this light here. Notice that the objects have the same brightness in a specific spot. It's just that the one I move further away is smaller. For example, if the total amount of light hitting the camera is f and the area that the light source takes up is omega, the surface brightness is f divided by omega. Now let's move the phone back so it's a fourth the size. Well, that means the amount of light hitting the camera is a fourth the original light, and the area it takes up on screen is a fourth the original size. So the fours cancel out and we end up with the same original surface brightness. So when you see a star in the sky, that brightness is actually about the brightness of the sun, but it's just taking up a tiny little pinpoint of space in your field of view. And so it doesn't seem as bright, even though that single point is as bright as the sun or brighter. So every point in the sky would therefore have roughly the surface brightness of a star. In other words, the night sky should literally look like the surface of the sun. This paradox had puzzled astronomers for centuries. Since the 1500s, many people believed the universe was infinitely old and infinitely large. Great thinkers like Johannes Kepler and Edmund Halley wrestled with this question. And in 1823, Henrik Olbers published a well-known discussion of it. His name became attached to the problem, and today it's known as Olbers' paradox. So what is the solution to this? Well, the answer began to reveal itself when astronomers started questioning one of the paradox's biggest assumptions. What if the universe wasn't actually eternal? In the early 1900s, we discovered that the universe wasn't infinitely old after all. So maybe the sky is dark simply because the light from the most distant stars hasn't had enough time to reach us yet. But unfortunately, that doesn't solve the paradox either. The reason is because the early universe didn't look like random stars just popping into existence. In fact, it was even weirder. Right after the Big Bang, the universe wasn't mostly empty like it is today. Instead, all of space was filled with an incredibly hot, dense plasma. Everywhere you looked was glowing plasma. So if we look far enough back in time before there were any stars at all, we shouldn't see darkness, we should see that hot glowing plasma in every direction. So we're right back to where we started. The night sky should still look like the surface of the sun. But then once again, why is the sky so black then? Now before we continue, I want to show you a tool that I've actually found useful when researching videos like this. A lot of my videos start with scientific papers. The problem is that there can be hundreds of papers on the same topic, and it takes a long time to figure out what the overall evidence actually says. So this video is sponsored by Consensus. It's an AI-powered search engine that searches more than 220 million peer-reviewed papers and gives you an evidence-based summary, along with the links to the original studies so you can verify everything yourself. One feature I like is the consensus meter. Instead of highlighting just one paper, it gives you a quick picture of where the overall body of research points. You can also filter by things like study type or publication date if you want to dig deeper. I think it's especially useful for literature reviews or checking the evidence behind scientific claims before you repeat them. So if you'd like to try Consensus yourself, you can get a free 1-week trial of Consensus Pro with no credit card required using the link in my description. And thanks again to Consensus for sponsoring this video. Now let's get back to our experiment. Well, the final piece of the puzzle came later when we discovered that not only is the universe not infinitely old, but it's also expanding. And an expanding universe does something really strange. It basically steals energy from everything. More accurately, as light travels through the expanding universe, its wavelength gets stretched. Longer wavelengths carry less energy, so every photon gradually loses energy as the universe expands. Eventually, the wavelength becomes so long that the light leaves the visible spectrum altogether. So all of the visible light that we should be seeing from the hot plasma that once filled the entire universe has been stretched into the microwave range. And sure enough, guess what we see when we look in every direction in the sky? We see microwaves. It's almost exactly what early astronomers predicted, a glowing sky in every direction, except instead of visible light, it's been stretched into the microwave part of the spectrum. We now call this the cosmic microwave background. No matter where you look, you see it. The sky really does glow in every direction. It just glows in a color our eyes can't see. But just how black is this blackness? So in the city, the night sky can be around 1 lux, which looks something like this. But if you're out in the middle of nowhere, far from any light pollution, the brightness between the stars can drop to only about 0.3 millilux. So what would that look like? Well, it turns out that it's so little light that after your eyes fully adapt, your own visual system becomes one of the limiting factors. And something really interesting happens when we block out all the light possible. So let me show you what this blackness looks like. Turn off the lights completely and cover your eyes so that no light can reach them. So the color you're seeing right now isn't actually pure black, it's called Eigengrau, or intrinsic gray. Compared to true black, it looks something like this. So Eigengrau is the darkest color that we can physically perceive. We can't actually see true black. The reason is that the rods in our eyes don't only respond to light. Every so often, random thermal motion inside the retina activates them even when no photons are present. So your brain interprets these random signals as a faint gray instead of perfectly black. So it's as though we're constantly seeing a very, very dim light everywhere in our vision. So in the end, the early astronomers were right to question why the night sky was black. It turns out they were right in more ways than one. The universe isn't truly dark because it's still filled with the glow of cosmic microwave background. And even if there were no visible light at all, our own eyes would still refuse to let us see perfect blackness. And thanks for watching another episode of the Action Lab, and we'll see you next time.